motor can produce that torque requirement. Let's say, for example, so in this case we are given all the parameters, and then we have to calculate starting torque. So if I go back to this, so I'll draw the equivalent circuit again. So this is the example question. We have so this is the equivalent circuit of the induction machine, and then this is fed from, so we assume that it's star connected, so that means the voltage across these two terminals, this is a per phase equivalent circuit. Then this voltage will be 415 over root 3, that's the phase voltage. And this element is R2 prime 1 minus S over S, and this is R1 plus R2 prime, this is X1 plus X2 prime, and this is the core loss resistance R0 and X0. So all this information is given. So we want to estimate how much torque it's going to produce. So if when you are looking at the starting condition, so starting condition, the rotor speed is 0. That's, the shaft is not rotating, so that's 0. The synchronous speed, you have some synchronous speed. This is not 0. That depends on the frequency. This is the excitation frequency. That depends on the frequency. So the slip will be ns minus nr. That's the slip divided by the synchronous speed. So for starting conditions, the nr is 0. So the slip will be 1. So that means the resistance here will be 0. If you put 1 here, it will turn out to be 0. So if we look at the electromechanical power that the motor is going to produce, so let's say if you have a current in this branch I1, so we can write the electromechanical power as I squared R, so that's I1 squared R2 prime 1 minus S over S. Since you have 3 phases, we multiply this by 3 as well. So this is the electromechanical power equation. So if you consider this for the starting condition S equals 1, the electromechanical power turns out to be 0. So there's no this equation doesn't give you the electromechanical power. It says it's 0. But then we need to find torque. So we can write the torque produced at 0 speed is equal to the power that's being transferred divided by the rotor speed. This is the rotor speed in radians per second. And then if you substitute this, we have 3 times I1 squared R2 1 minus S over S divided by the rotor speed. So this is 0 as well if you are looking at the S equals 1 condition. The rotor speed is 0. So this, if you substitute S equals 0, this is 0 and this is 0. So it turns out to be 0 divided by 0, which we can't calculate. So one of the so we can actually substitute this in terms of the excitation frequency. Let's say the omega r, we can write it as 1 minus S over the synchronous speed. So if it's rotating at a certain synchronous speed, this is the speed. If it's S equals 1, this turns out to be 0 anyway. But then if you substitute this here, we find this 3 times I1 squared R2 prime 1 minus S over S divided by 1 minus S over synchronous speed. So then the torque, this cancels out. So you can write the torque expression as simply this with this expression. That's 3 times I1 squared R2 prime. So there's a prime here as well. divided by slip over omega s. So actually the torque equation doesn't have a 1 minus s term within it anyway. So if we bring slip down to 1, then this becomes 1. So that's the starting condition. So if we look at the starting torque, you substitute slip equals 1. So that will be 3 times I1 squared R2 prime divided by omega s. So here omega s is the synchronous speed. The shaft is not rotating, but then we substitute the synchronous speed here because we've done this type of cancellation. So to find the starting torque, we need to figure out the current in the circuit when it's starting. So at starting conditions, this is 0 as well. So the whole thing turns out to be 0, and then you have just these two elements in this. So the starting current is this voltage divided by this impedance here. So if we substitute the values, for this particular example, we have 0.3 here, and this is given as 0.4, and this is given as 0.5, and this is given as 0.7. So the whole this whole impedance, we can write that as let's say Z. We can write that as 0.3 plus 0.4 plus J 0.5 plus 0.7. So to find the starting current, we are interested in the magnitude of this impedance. We don't need to know the phase. So this is 0.3. So this turns out to be 1.389 with phase angle 57.74. So we are only interested in this particular magnitude of the impedance. So the starting current, I start, that's this particular voltage divided by the impedance of this branch. So that's 415 over root 3 divided by 1.389. So this turns out to be 172.47 amperes. So that's the starting current. So now if we substitute this here, you'll get the starting torque for the induction machine. So starting torque, T start, starting will be 3 times 172.47 squared, and R2 prime, that's given as 0.4 ohm. So 0.4 divided by the synchronous speed. So in this example, it says it's a 50 hertz 4-pole induction machine. So then the synchronous speed is going to be, I think we calculated that before, the synchronous speed would be 3000 divided by 2, so 1500 RPM. So that's 1500 synchronous speed times 2 pi over 60 to get the mechanical synchronous speed. So we have 227.24 Newton meter starting torque for the given induction machine. So the next tutorial, you'll be working through some examples in relation to the induction machine calculations. So this is the tutorial. I've updated it on Canvas, so you'll probably see this later today. So I've moved some of the tutorials to another PDF file saying supplementary examples. So those I'll try to cover in the lecture. These questions will be attempted by the tutor next week in the tutorials. So these questions you are given the equivalent circuit parameters, and then you have to figure out certain characteristics like speed, torque, slip, and so on. So one of the next topic is to figure out what tests you can do on the induction machine to figure out these parameters. So it's fairly similar to the transformer tests. So in the transformer, we did like two tests. One is the open circuit test and the short circuit test. So in this example, it's fairly similar. So if you lock the shaft, let's say locked rotor condition, the slip is 1. So slip equals 1 means this is 0. This here it's 0. So that's like a short circuit condition on the equivalent circuit. So then the majority of the current will flow through this path. So that with that test you can determine these two elements. If you were to run the machine at really close to synchronous speed, that means slip is almost 0. So that means this element here will be in close to infinity. So very large value here. That's like open circuit test on the transformer. So majority of the current will flow through these two branches, and then from that information you can estimate these two values. So you can kind of when you remember the tests you do on induction machine, you can have an analogy with the transformer tests as well. So if you compare, let's say the first one is like the locked rotor test, or you write it as locked rotor test. So this is similar to the transformer short circuit test. So in the induction machine, we have here this type of equivalent circuit, and for the transformer we had a similar circuit as well. So this is for the transformer, and then this is the primary and the secondary, and the transformer we short circuit the secondary. Here we bring this to 0. So R2 prime 1 minus S over S. S equals 1 means this whole thing will be 0. So that's equivalent to the short circuit test of a transformer. So then majority of the current flows through this path, similar to the short circuit test of the transformer. So one of the assumptions is that we neglect the power losses in these two elements. So then from this test we estimate the equivalent resistance and the leakage reactance, similar to the transformer Q and REQ. So you do two measurements. One is the real power measurement. So one measurement we have is P real power locked rotor real power measurement. This is from a wattmeter which you connect in series with the circuit. You can get the real power that you put into the induction machine when the rotor is locked. And then you can also measure the voltage. Let's say lock rotor. This can be a phase voltage or a line-to-line voltage, and you can also measure the current going into this circuit as well. So that's the lock rotor, lock rotor current. So these are the three measurements that we obtain during the tests. lock rotor test. So from these two values you can estimate the apparent power. So from this you can figure out apparent power is lock rotor, and then so you have the real power measurement, you calculated the apparent power measurement, and then you can find the reactive power measurement. Lock rotor reactive power will be the lock rotor apparent power squared minus P lock rotor squared square root. So this will be the reactive power measurement. So then your real power measurement will correspond to the power losses in this particular element. That's the series resistance, winding resistance. And the reactive power will correspond to the leakage reactances. So then you can write P LR, that's the real power measured during the lock rotor test, is equal to 3 times R EQ I lock rotor squared. So this is the real power measurement. We've measured this, we've measured the current as well. So then you can figure out the resistance REQ from that lock rotor test. So REQ will be P lock rotor divided by 3 times I lock rotor squared. So mind that this has to be the total 3-phase power. If you measure per phase power, then you don't have the 3 here. So it depends on the circumstance. If you measure just per phase power, and if you're given just the power consumption per phase, then this will be just REQ I squared. You won't have 3 times. 3 times comes because of 3 phases. So mind that depending on the information given. And this we can write Q lock rotor will be 3 times XEQ I lock rotor squared. And then you can find the XEQ with Q lock rotor divided by 3 times I lock rotor squared. So that's the lock rotor test. So you can see the similarity in the calculation with the transformer short circuit test. So the other test is when you bring the speed up close to synchronous speed, we'll have SC close to 0. So that's like the open circuit test. But then one of the complications is that when you're running, if you powered up the induction machine and then you haven't connected any load to the shaft, it will spin close to synchronous speed, but then you'll have rotational losses. So the if you run it under no load, then you have rotational losses plus the core losses as well. So that's a complication. Let's say no load test. So we have the same circuit, and now this is running at some value where S is close to 0. So the power consumed in this element will be equal to the rotational losses. So PEM equals P output plus the P rotational losses. So when you're running it no load, that means this is going to be 0, and your PEM will be the rotational loss value. So you are running it no load, so the total power that's being transferred to the rotor is the rotational losses that you need to compensate. So so if you run it under no load, you have these rotational losses plus the so let's say we've powered this up and this is running at no load. So the impedance of this path is fairly large compared with this path. So the current here is really small compared with the current in this branch. So it's similar to the assumptions that we make in the open circuit test. So then this current, let's say I'll write it as the magnetizing current, is really large compared with I1 in this case. So then we can assume that the power loss, this power loss in this is negligible. The power loss in this element is negligible because the current in this branch is small. This will be really small, but then you'll have this power, which is a certain amount of power being consumed in this element. So you'll have some real power consumed in this element. That's the core losses. This is the core losses. So now if you run it under no load and then measure the power you put into the machine, let's say you measure P no load. P no load will include the core losses, the losses in this plus the losses in this part as well. But then we assume this is negligible, so we assume this is 0. So we can write P no load is equal to the core losses, let's say core loss plus P rotational losses. So in order to calculate, so the objective is to calculate these two elements from this test. So in order to calculate that, we need to figure out this value here, the core loss value. So in certain instances, let's say you don't know the rotational losses, and if this is fairly small, one assumption is that you can neglect the rotational losses and assume the no load losses is equal to the core losses, and then calculate the value here. So that's, if you don't have any other information, you can do that. So then it's fairly similar to the short circuit test calculation. So then P rotational losses, we assume it's 0. And then we can say that if you are supplying a certain voltage here, let's say the phase voltage, no load, you'll have the no load power is equal to the no load per phase voltage squared over R naught. And since this is per phase, you'll have 3 times this if you're measuring the total power input into the induction motor. So in some instances, we can write this, if it's a star connected induction machine, this is the per phase voltage, and we can write the line to line no load voltage as root 3 times the per phase no load voltage, and then the line to line voltage squared will be 3 times no load voltage per phase voltage squared. So we can also write this as the line to line no load voltage squared over R naught. This will be the total power input. So let's say this test, if you connected it in star, let's say if the induction machine is connected in star, one of these circuits is represented by one of these elements, and then the voltage I drew here is the voltage across this per phase voltage, the no load, and this will be your the no load line to line voltage, which is root 3 times the no load. So then your power P no load, that's the total 3-phase power, will be the line to line no load squared over R naught. That's from this expression here. You have 3 times V no load per phase divided by R naught, and then you factor in the root 3 here, and then it will turn out to be line to line voltage squared divided by R naught. But then that's for if it's star connected. So this is all for a star connected induction machine. If you were to connect the induction machine in delta arrangement, let's say if it's connected in delta, this is the no load voltage you are applying, and the line-to-line voltage will be the same as the no load voltage. So this is the line-to-line no load. So if it's delta connected, your line-to-line no load voltage will be the phase voltage as well. It's the same voltage. So then P no load will be 3 times V line-to-line no load squared over R naught. So that's for a delta connected arrangement. So you have to mind the difference if whether it's star connected or delta connected. If you stick with the phase voltage, 3 times the phase voltage, then it's applicable for both cases. So this is for delta connection. So in general, I'll write P no load is equal to 3 times the no load voltage. So this is the per phase voltage squared over R naught. So this can be the per phase voltage or line-to-line voltage, depending on whether it's star or delta. So then you have this information, you are measuring the line-to-line voltage as well, and then you can figure out the core loss resistance by 3 times V no load squared over the measured power there. So the core magnetizing reactance calculation is the same approach as well. So we can write the Q no load as 3 times V no load squared over R naught, and then we can figure out the magnetizing reactance as 3 times V no load squared over Q no load. So determining Q with the voltage and the current you feed into the machine, you can determine the reactive power. So that's the test, no load test, and you assume the rotational losses are negligible. So no load means you powered up the induction machine and it spins without any load. So there's another test that's more accurate, that's called a zero slip test. So zero slip test, you artificially drive the shaft at synchronous speed. So that's the other test, it's a zero slip test. This is complementary to the no load test. So then you have the induction machine, and this is connected to the voltage source, and you have the shaft, and this is previously we didn't connect anything under no load. This is just open and it spins close to synchronous speed. But then zero slip test, we let's say couple it to another machine. Maybe this is a variable speed machine, and then we drive this exactly at synchronous speed. So this will be running at 1500 RPM, let's say for example for a two-pole pair 4-pole machine. For example, this is controlled to run this shaft at exactly synchronous speed. Then in your equivalent circuit, this will be S will be exactly 0. So previously S was close to 0. That means there was a large value, but it consumed some power. But then if you were to drive this exactly at synchronous speed, the S will be exactly 0. So that means this will be really large. It will be infinite. So then it's exactly the same as the open circuit test of a transformer. So then you can assume that this whole branch is not there. It's open circuited. So then P in will be exactly the core losses. Let's say measured rotational losses. Q lock rod, say zero slip test. Let's say P and Q will be, this is the core losses, and the reactive power will be V no load squared over X naught. This will be exactly the V no load squared over R naught. So in this test, you can see that this is feeding in certain amount of power. The other machine is compensating the rotational losses by driving it at the synchronous speed. So effectively, this the other machine is feeding in P rotational losses, and this machine is feeding in the core losses. And we are measuring the power, reactive power from the induction machine side. This is the induction machine, and this is some other machine which drives it at synchronous speed. Any questions on the tests on induction machines? So there's a PDF file on Canvas that says supplementary questions. That's this one. It has one question on the testing procedure. So this, okay. So the first question, it's you have a test on a 4-pole 415 line-to-line 3-phase star-connected 50 Hz induction motor gave the following results. So you have a no-load test. You are given the power consumption, the current, the voltage. This is taken at synchronous speed with the drive motor supplying the rotational losses. So effectively that means this is the zero slip test. Lock rotor test, you have this information. So the objective is to figure out the equivalent circuit parameters. So I'll give you a couple of minutes to try it out. finished. All right, so fairly similar to the transformer calculations. So we are given the line to, so it says it's a star connected induction machine. So it's connected like this. So this is question 1. And you're feeding in for the, if you look at the lock rotor test, we are feeding in 415 volts. So that means that's the voltage. And per phase voltage is 415 over root 3. And the line current is given as 10 amperes. This is for the no load test. And then it consumes 0.5 kilowatt per phase. So one phase consumes 0.5, and P no load, let's say for the total power, that which will be 1.5 times 3, so that will be 0.5 times 3, it will be 1.5 kilowatt total power. And the apparent power will be, let's say S no load, will be the voltage root 3 times the line-to-line voltage times the current. So we can write root 3 times V line-to-line voltage and I line current. That's the apparent power, 3 times 415 times 10. So that will be that will be 7.188 kVA. That's the apparent power. And the reactive power, Q no load, will be S no load squared minus P no load squared, square root. That will be the reactive power. So we have 7.029 kVAR, that's the reactive power. So now you have the reactive power as well as the real power. So we can find the for the no load test. So the branch here, we assume that's open circuit. It's running at synchronous speed, so S equals 0. So that's like an open circuit there. And then our objective is to find these two elements, R0 and X0. So we can write this is the no load voltage. So since it's star connected, we can write P no load will be equal to 3 times V no load squared over R0. So here we can write this as the line-to-line voltage squared. So that will be 415 squared over R0. This is equal to 1.5 kilowatt. So then R0 will be 415 squared divided by 1500. Which is 114.8 ohm. So that's the core loss resistance. Similarly, we can write Q no load as 3 times V no load squared over X0. So then we can find X0 with 3 times V no load, 415 squared divided by the reactive power, which is 7029. So that's 24.5 ohm. That's the reactance, magnetizing reactance. So that's all from the no load test. So the next one is the lock rotor test. So then we lock the rotor, the slip equals 1, so then this point is like a short circuit in that condition. And then we neglect the shunt, the branch here, we neglect for that one. So this one we neglect under that condition. So for the lock rotor test, the line-to-line voltage is given as 150. So we have 150 over root 3 here, and the current is given as 40 amperes. So here we have a 40 ampere current, and the power that it consumes is given as 1 kilowatt per phase. So P lock rotor will be 3 times that. The total 3-phase power will be 3 times 1 kilowatt, so 3 kilowatt total input power, and the total apparent power for that operating condition will be root 3 times line-to-line voltage, which is 150 times 40, that's the total apparent power. So I'll write it as kilowatt, so that will be 10.392 kVA, that's the apparent power. And then we can figure out the reactive power, that's this S squared minus P squared, so 10.392 squared minus 3 squared square root, that will give you the reactive power. So that will be 9.9499 volt ampere reactive kVAR. That's for the total reactive power. So for the lock rotor test, the power consumption is I squared R here for real power and I squared X for the reactance there. So we can write P lock rotor power will be 3 times I lock rotor current squared R EQ. That's for the element here. So we can write REQ as P lock rotor divided by 3 times I lock rotor squared. So that will be the 3 kilowatt divided by 3 times 40 squared. Which is 0.625 ohm. That's for the copper resistance. And then similarly, the reactive power, we can write lock rotor as 3 times I lock rotor squared X EQ. So the reactance will be Q lock rotor divided by 3 times I lock rotor squared. So that will be this value, 949.9. That's the reactive power divided by 3 times 40 squared. That gives you the equivalent leakage reactance. Which is 2.07. So that's the characterization tests of induction machines. Any questions up to that point in relation to the testing methods? It should be fairly easy at this stage since you've done like transformer characterization tests, isn't it? So it's pretty much the same concepts. just have to think of the lock rotor test as a short circuit test and the no load test or the zero slip test as the open circuit test. So the next topic is on braking methods of induction machines. So when you are spinning, let's say when you're running an induction machine, you want to, let's say you can turn the induction machine off simply. So if you just turn it off, it will spin down to zero speed. But then let's say if it's a strain or some other application where you want to brake the system, let's say stop it really fast, then if it's a DC motor, you would actually interchange, let's say apply a negative voltage and then work it as a generator. Similar concept can be applied to induction machines as well. So instead of changing polarity, we can change the synchronous speed. You can flip the synchronous speed the other way. Let's say if you are feeding the induction machine phases with, let's say, phase sequence A, B, C, if you change two terminals of the induction machine, the synchronous speed will be negative. So let's say you have let's say three phases. This is feeding, you are connected VA, VB and VC to these three terminals. And this is the induction machine, and let's say the field rotates in a certain direction, let's say this direction, that's your synchronous speed, omega s, for this particular phase sequence. Let's say if you were to flip two of the terminals, interchange two of the terminals, let's say if you connect VA and then VC and VB here, if you interchange two terminals, the synchronous speed will reverse. So this reversal is instantaneous. It's the electromagnetic field. But let's say in this case the shaft is rotating at a certain direction, omega r, for example. It's spinning, let's say this is synchronous speed. Let's say, for example, if it's a two-pole 50 hertz machine, two-pole pair 50 hertz machine, this will be 1500 RPM, and I'll just plug in some number, let's say 1440 RPM, for example. The rotor is rotating at this speed. The synchronous speed is 1500. So then you have a slip of 60 divided by 1500, which turns out to be 0.04. So let's say this induction machine is operating at this particular condition. Let's say you suddenly interchange two terminals. You flip VB to VC and VC to VB, this arrangement. The field, the direction of rotation of field will instantaneously turn the other way. But the shaft has inertia and then it's connected to a load, so it doesn't change instantaneously. The shaft will be still rotating. Let's say this is the shaft, and then this is still rotating at 1440 RPM at the instant you interchange the two terminals. This will change instantaneously, so now the speed will be negative 1500 RPM. So now your synchronous speed is negative, but the motor is spinning the other way. So this condition is like a generating condition. It will start generating back into the system, and the torque that you produce will be negative, so it will spin down really fast. The slip for this condition will be, the synchronous speed is now minus 1500. The rotor speed is minus that speed, 1440, divided by synchronous speed again, 1500. So then you'll have 1500 plus that, so that's minus 2940 divided by 1500. So the slip turns out to be 1.96. So by interchanging two terminals, we've immediately converted the slip from 0.04 to 1.96. So then the machine will decelerate, it will spin down to 0. If you keep it connected the same way, it will start spinning the other way. So it will turn the other way. Otherwise, when it spins down to 0 speed, you just turn off the power, then it will stop. So this method of braking is called plugging braking. So this is called plugging braking. I think you had one question on this on the tutorial. Yeah, so in the sixth tutorial, question 4, you had some information question related to that, like if you were to plug, that means you interchange two terminals, what would be the synchronous speed be? So that means the synchronous speed will be negative. At the instant of plugging, you'll have a really high slip value here. So the shaft is spinning clockwise, the field is spinning the opposite direction. So that's this calculation here. So if you look at the torque speed profile, let's say, I think you've come across the torque speed profile before for induction machine. It's something like this. So this is speed, and then this is torque. This is the zero speed condition. This is speed equals 0, and that means slip equals 1. This is speed equals, let's say, synchronous speed. Let's say, for example, for a two-pole pair machine, this will be at 1500 RPM, and slip will be 0. So at synchronous speed, it's not producing any torque. So a normal operating point will be somewhere here, let's say 1440, and you are operating it at this point. So this is for, let's say, a certain phase sequence. If you were to reduce it to 0 speed and start spinning it the other way, let's say you artificially connect it to another machine and then you try to rotate it the other way, the torque speed profile will extend towards the negative region as well. So this is positive speed. You've excited it with ABC, let's say this phase sequence ABC, and then this is the normal operating region. If you were to artificially rotate the shaft in the opposite direction, this will be the torque it will produce at that condition. If you were to interchange two terminals, if you plug the machine, the torque speed profile, you'll be spinning at synchronous speed somewhere here. So then your profile will be something like this, I guess. So this is when this is for VA, VB, VC sequence, and this is for VA, VC, VB sequence. It's spinning the other way, and it's producing. If you keep it that way, it will eventually produce negative torque and then negative speed. That means it starts spinning the other way. So if you were to immediately interchange the two terminals, the operating point will go from here to this point immediately. So it will be producing positive torque, and then suddenly you interchange two terminals, then immediately you'll have negative torque on the machine. That's the value you get here. So that's that in relation to the torque speed profile. So this torque speed profile, you can plot it. If you have the equivalent circuit parameters, you'll be able to plot it with that equation as well. So I'll also go through the supplementary question, the second question of that as well, before I move on. So any questions in relation to this braking method of induction machines? Yes?
Just one question. A plugging brake, when you reverse polarity to a vehicle,
Yes, yeah.
say if you did it with contactors and like you didn't have a VFD or anything, find it to pump that current back into the grid, or do you need braking resistance?
So at the point of when it's running, it will be conducting some current. So let's say you let's say you disconnect it, then it will spark over, I guess. So you need to have some form of high capacity contactor to disconnect it under load conditions. And then you interchange it and then connect it again. And then I don't think you need any resistances.
But so it's fine. So like, you know how you said it was operating as a generator, it's fine to just have that. Obviously for like a 1 kilowatt motor, it doesn't matter to pump that back into the grid.
Yeah, no, it doesn't matter. I don't think so, no. If it's the worst that will happen is that at the point where you connect to the grid, your voltage will be slightly higher because you are feeding in power. Yeah. So I'll move on to the other question in the supplementary examples. It's pretty much the same. Is it the same question as we did before? Yeah, this is the same question I did in the beginning. So I'll not do that then. This same numbers and the same question. Yes, this is the same question I did that's in the lecture slide as well. So, as I mentioned, so let's say if you were to be given this information, you'll be able to plot the torque speed profile as well. So, you can try it out in MATLAB, for example. So you have these parameters, rotor resistance, and everything. So if you were to let's say we put in all the values here. So we have R1 is equal to 0.3 and R2 that's 0.4 and X1 is equal to 0.5 and X2 is equal to 0.7. So let's say you assume the slip is 0.04. Then your voltage, the line-to-line voltage, let's say phase voltage will be 415 over root 3. So that's the phase voltage. And we can find the impedance of the current, the torque producing branch. That will be R1 plus R2 plus x1 plus x2 plus you have another, the variable resistance, which will be R2 1 minus S divided by S. So this will give you the impedance. So let's say if we run it Okay, so that's the impedance, and then we can find the current. Let's say I1 will be the phase voltage divided by Z. So that will give you the current. So we are interested in the magnitude of it, so we'll write it as the absolute value of that. So then I1 will be this. Is that the answer we got from the previous question? So we can also find torque, or we'll find PEM. That will be 3 times I1 squared times R2 times 1 minus S divided by S. And the torque, electromechanical torque, is the electromechanical power divided by speed, which is 1 minus S times the synchronous speed. So the synchronous speed, let's say NS was 1500. It's a 4-pole induction machine. So we can write this as Ns times 2 pi over 60. So that will give you the electromechanical torque. That's 101.96. So that's the value we were able to calculate before, close to 102. So that's one operating point. So if you were to vary speed, let's say, then you can plot the torque and speed profile. Let's say if we write this as NR, that's the rotor speed, we'll write this term here. That's the speed in terms of RPM. And then we will divide this by NR. So if we were to change the slip or the speed, then you'll be able to plot this. So we'll say S in terms of if a parameter here, let's say S equals NS minus NR divided by NS. and this is our variable, which we can put anything, let's say 1200 for example, and then you'll have some torque value for that particular condition. So then, let's say if we iterate through this program, you'll be able to say find a torque for different range of values. Let's say you start off with 0 and then go up to 1500, and then we store the torque and speed values. Let's say you've calculated torque here, so we'll store that somewhere here, and speed and in R. So then you'll have a range of values. And then you can plot the torque, speed and torque. I think this is taking too long. I'll probably do like increments of 10 maybe. So okay, so that's the torque speed profile for that particular machine. So you can even go to negative speed here as well. So let's say if you do negative 1500 to positive 1500. So this is 0, and that's the variation of torque speed, and this is the starting condition around here. That's the starting point. And then if you were to reverse the synchronous speed, let's say you've interchanged, plugged it, and then that will be negative. So then your torque speed profile will be the one similar to the one I drew earlier, I guess, or something like this. So this is for the VABC sequence, ABC phase sequence, and this one will be for the ACB phase sequence. So this is 4 quadrants. One is positive torque, positive speed. This area is for positive torque, negative speed. This area is for negative speed, negative torque. So that means it's spinning backwards, motoring. This is for positive speed, negative torque. It's again generating. So this is motoring, and this is generating, and then generating here. So those are the 4 quadrants of operation of the induction machine. So keeping that in mind, let's say if we can also operate the induction machine with a variable frequency drive as well. So modern, let's say, variable speed drives, you don't operate exactly at using 50 hertz. You have an inverter which excites it at different frequencies, let's say 50 hertz or 40 hertz or lower or higher. So that variable speed operation will change the synchronous speed. So let's say if you were to change the synchronous speed, so 1500 was for 50 hertz. So let's say we can write this as 50 times 60 divided by 2. So that was for 50 hertz. But if you were to change frequency to 40 hertz, for example, you'll find that the torque speed profile shifts and the peak point here goes up a little. If we change it to 30 hertz, that's the synchronous speed is now changed to a different value. It shifts up and then goes backwards a little. So the synchronous speed is here for 30 hertz. around here for the 40 hertz, and then around here for the 50 hertz, and so on. So, but then we have a problem when you change frequency, but not change voltage. So, if you look at the equivalent circuit, so now this topic is on variable speed operation of induction machines. So if you look at the equivalent circuit of the induction machine, you have this form of circuit, and you are feeding this with a certain voltage, the per phase voltage. Let's say this reactance and this reactance are functions of frequency. So this will be X, the reactance will be some inductance times omega S, this corresponds to the excitation frequency, as well as this reactance, that's the magnetizing reactance, that will be the magnetizing reactance times S, or this will be the same as Lm2 pi Fs. So in the case you are supplying it at 50 Hertz, this will be 50 Hertz. So if you look at the current going into this branch, let's say the magnetizing current, so the magnetizing current is important because that's the current which magnetizes the core and establishes the field in the induction machine. So the magnetizing current Im will be the phase voltage divided by JLm 2 pi Fs. So let's say you reduce the frequency of the induction machine, you still supply it at the same voltage, and you reduce the frequency, so this value goes down, so this is fixed, and this goes down, the current will go higher, so the magnetizing current will increase. So that's not good for the induction machine. So if you increase the magnetizing current, it tends to go into saturation region, so it's not designed to operate at that conditions. Although in this graphs we saw that the peak torque point increases. At some point you won't be able to operate the machine because it's saturated. So we like to keep this magnetizing current constant when you change frequency. So to do that, so if you look at this, frequency is the one we change, so we can also change voltage. So if we were to have, let's say, 1 over JLm 2 pi, and then V phase voltage over Fs. If we were to keep the voltage over frequency constant, if we change frequency by half and if we change voltage by half as well, the magnetizing current will remain the same. So when you're operating the induction machine under variable speed conditions, we keep V over F constant. So that's called V over F control. V over F control. So that means we keep V over the phase voltage divided by synchronous speed, the excitation frequency constant. The main objective of this is to keep the magnetizing current constant. So it's magnetized at the same level under all frequencies, it's not going into saturation. And the peak torque that you can produce in the induction machine, it will be fairly the same because the magnetizing current is the same as well. So in this, the plots that we did earlier, we had like when we were not changing the magnetizing current, when we were just changing the frequency, you had, let's say this is the normal operation, and then you had something like this, and then something like this. So this peak point, so this point is called the pull-out torque. So the pull-out torque value increases with frequency. If you change frequency changes, and the phase voltage is fixed. But if you were to change phase voltage and frequency at a constant ratio, you'll find that this profile will have like roughly the same peak pull-out torque value. So this is for V over F constant operation. This is the speed and torque. So this was the plot we had earlier. So this is for nominal, let's say 50 Hertz. This was for 40 Hertz and 30 Hertz. And we kept the voltage fixed. So here the voltage is fixed at this point here. But then if we were to change the voltage as a ratio of frequency, let's say we say frequency here, Fs is 50 Hertz, and this is Fs. This is your synchronous speed, and then if we change, this is at 50 Hertz, 415 over root 3 will be at 50 Hertz. So then we want to change it, reduce it when we reduce frequency as well. So then we'll multiply it with the frequency and divide by 50. So if it's 50, you get 415 over root 3. If you reduce the frequency, the voltage will reduce as well. So at 50 Hertz, you'll get the same profile as before. That's your 50 Hertz profile. And then if you do 40 Hertz, So this was for 50 Hertz. We are doing from this particular speed to this speed. So we'll probably do from minus, let's say 0 synchronous speed to synchronous speed. Let's say for 50 Hertz we have this, and then for 40 Hertz you have this profile, and then for 30 Hertz so made a mistake. Do you know why this profile is not the same as what I drew before? What I drew on the paper was having similar peak torque values, but then this shows it's reducing. So these X values are a function of frequency as well, so we need to change those as well. So this X value is for 50 Hertz, so that's like 2 pi F times the inductance. So we have to scale these values by 50 Hertz as well. Let's say Fs over 50 for the reactances. With frequency, the reactance values will change as well. So if it's 50 Hertz, you have this, and then 40 Hertz. It's fairly similar peak torque, and then 30 Hertz. 20 hertz and so on. So you don't have increase in peak torque, so fairly the peak torques are fairly in roughly similar range. So the important characteristic of this VOF control is the region here where you're operating around here. So if you look at these lines are parallel to each other. This from here to here, it's parallel to this, all this around here, around this region, it's parallel to each other. So we are interested in that characteristic when you're operating VOF control. So if you look at the torque speed characteristics when you're operating VOF control, constant, let's say I'll draw this one here and then something like this and then another frequency, let's say 3 frequencies. This is frequency 1, frequency 2, frequency 3. So you saw that in the profile, the line around here is fairly parallel to each other. So let's say, for example, if you want to, let's say this is 50 hertz normal operation, you're operating at this particular operating point and it's producing a certain torque. Let's say this point has a torque of, let's say TEM, it's producing a certain amount of torque. And this is your synchronous speed, NS1, and this is your operating point rotor speed, NR1. And the difference between these 2 points is the slip speed, so I'll call that N slip 1. So for this particular operating point, it's producing this amount of torque with this particular slip speed. So if you look at this operating point, it's producing the same torque, but then at a reduced speed. This is NR2, and the new synchronous speed is NS2. But then if you look at these 2 triangles, it's fairly the same triangle. So if the one triangle is here, one other triangle is here, but they are identical triangles. So the slip is therefore the same, and the height of the triangle is the torque. So this is the TEM, and this is N slip 1, and it's the same as N slip 2 in this second case. So if you are changing frequency with voltage, if you want to achieve the same torque, the slip has to be the same as well. So that concept is used if you want to operate the machine at a certain load condition. Let's say, for example, you might be given at 50 hertz, the induction machine produces this amount of torque, and it's excited at 50 hertz. Let's say, for example, if it's a 4-pole machine, this will be 1500. And then let's say the slip is 60, and the shaft is rotating at 1440, for example. And let's say, for example, this machine is producing 100 Newton meter of torque. Let's say you want to operate the machine at, you're given, you want to operate the machine at 1000 RPM. You want the speed to be 1000 RPM, and you want to have a torque of 100 Newton meter here as well. And then you ask to figure out the voltage and the frequency you need to excite the machine at. So then from this triangle to 2 triangles, you know that this triangle, the slip is 60. So then the slip in this triangle has to be 60 as well. And then the synchronous speed will need to be 1060 RPM. So the synchronous speed of the new condition is 1060, and that corresponds to frequency as well. And the voltage and frequency, we change it at a certain ratio. So you can figure out if this point is at 415 volts, this point will change according to that ratio. So that's the V over F control method. The supplementary example, any questions on that VOF control aspect? So the supplementary questions, the third question, says a three-phase 50 Hertz 4-pole 5 kilowatt 415 induction motor has a full load torque speed of 1455 RPM. It is driven by a variable frequency supply operating with constant voltage over Hertz. That's VOF control characteristics. Plot the torque speed characteristics in the neighborhood of the corresponding synchronous speed when the motor is supplied by frequencies 50, 40, 25 and 10 Hertz. So let's say this is the Q3 of that supplementary question. So it's similar to what I drew earlier. So normal operation, it's something like this. This is at 50 Hertz and 415 volts, 50 Hertz. And then if you reduce the frequency and voltage, it will be somewhere here. This should be lower a bit, so maybe something like this. So, and then this will be at 40 Hertz. And this point, it's given as a 4-pole induction machine. So if this point will be 50 into 60 over 2, which is 1500 RPM synchronous speed. This point will be 40 into 60 over 2, which is going to be 1200 RPM. So we have to figure out the voltage. So if it's V over F control, the voltage will be, for this particular condition, the line-to-line voltage will be 415 times 40 over 50. So it scales down with frequency. 415 over 40 over 50 gives you 332 volts. So this will be fed by 40 Hertz, 332 volts. And the other frequency is 25 Hertz. So let's say somewhere here. This is at 25 Hertz. And the corresponding synchronous speed there will be 25 into 60 over 2, which will be 750 RPM. And the line-to-line voltage will be 415 over 25 over 50. So it's half the voltage, so that will be 207.5 volts. So if it's 25 Hertz, you need 207.5 volts line-to-line voltage. And similarly, let's say somewhere here, that's for 10 Hertz. The synchronous speed will be 10 into 60 over 2, which is going to be 300 RPM. And the voltage for that condition will be 415 over 50 times 10, which is going to be 83 volts. That's here. So these are the torque speed profiles for the different voltages and frequencies. So if you want to produce the same torque under all the different speeds, so this is your torque. So then if you look at these triangles, these will be all identical triangles for the same torque production. So let's say, for example, this produces 5 kilowatt. At this point, it's producing 5 kilowatt, and the speed is given as 1,455. This is producing 5 kilowatt, and the torque is 5 kilowatt divided by 1,455, 2 pi divided by 60, 1,455, 55. So this is 1,455 times 2 pi over 60. So the torque you have is 32.8 Newton meter. So let's say this is 32.8 Newton meter torque. So to produce 32.8 Newton meter at all the speeds you consider, here you have a slip of 45 RPM. This distance is 45. Let's say end slip is equal to 45 RPM. So then you need to have similar slips in all the operating conditions. So here it will be the operating speed here will be 1,200 minus 45. So here the operating speed will be 1,200 minus 45, and the motor will be running at 1,155. Here it's running at 450. So 450 minus 45, here it will be running at 405 RPM. And here again same concept. Here it's 300 RPM synchronous speeds, but the motor is running at a slip with 45, so then it will be 255 RPM. So these are the speeds the motor will run at if you load it at the same torque. So that's the V over F control concept. So there are a couple of examples in the tutorial 7, question 4 and 5. So next week the tutors will go over it in the tutorial sessions. So as the remaining time, I'll just briefly go through last year's exam question on induction machines, which will be interesting. Where's the exam question? So this was last year's exam question. So we have, it says 3-phase star connected 415 50 hertz 4-pole induction motor has a starting current of this value and produces a starting torque of 180 Newton meter. So you're given certain information. Part A, calculate the stator referred rotor resistance of the induction motor. So it's kind of working backwards from the concepts that we discussed. So you have to know how to define the starting condition. So this is from 2018 exam question. So if you look at the equivalent circuit, the starting condition, you have this. And this is the current I1. So it's like the lock rotor condition, and we neglect this bit here, and we assume this is consuming 116 amperes, and this is the PEM is going to be 3 times R2 prime I1 1 squared 1 minus s over s, and the torque is going to be 3 times r2 prime I1 squared over s times the synchronous speed. So for starting, s equals 1, so TEM starting condition will be 3 times r2 prime I1 squared over the synchronous speed. So we can figure out all these information, and then we have to estimate the rotor stator referred rotor resistance. So R2 prime will be TEM, the starting torque, times the synchronous speed divided by 3 times I1 squared. So we are given the torque, that's so we'll find the synchronous speed first. So we have 50 hertz, it's a 50 hertz 4-pole induction machine. So the synchronous speed will be 60 into 50 divided by 2, so that will be 1500 RPM synchronous speed. So if we substitute the values here, we have a starting torque of 180, and the synchronous speed is 1500 times 2 pi over 60, that's the synchronous speed in radians per second, divided by 3 times, there's a current of 116 squared. So this will be your stator referred rotor resistance. So you have 0.7 ohm for rotor resistance. So next part, the motor delivers 8 kilowatt load at a certain speed where the rotational losses are known to be 500 watt. The stator referred rotor current is given as 20 amperes. Part 1 of that, determine the electromechanical power developed in the motor and hence or otherwise calculate the slip at this operating condition. So again, it's working backwards. You are given a certain operating point, and it's producing an output power of 8 kilowatt, and that's the P out. So for part B, P out is given as 8 kilowatt, so that's 800 watt, and the rotational losses are given as 500 watt. So the total electromechanical power developed by the motor is 8500. That's the output power plus the losses. It has to produce this amount of electromechanical power. So this is for part 1. And then and hence or otherwise calculate the slip at this operating condition. So again, we can apply this particular equation. So we can write PEM as 3 times R2 prime I1 squared 1 minus S over S. So we have the PEM value, we calculated that here. R2 value, we've calculated it earlier, that's 0.7. Stator referred rotor current, that's 20 amperes here. So then we need to solve only this bit here. So we can write 1 minus S over S is equal to PEM divided by 3 times R2 prime I1 squared. So PEM was 8500 divided by 3 times 0.7 and 20 squared. So this turns out to be 10 0.119. So that's 1 minus s over s. So if we solve this, you'll get 1 minus s equals 10.119 s. You can bring this to the other side, so then it will be 11.119 s equals 1, and the slip will be 1 over 11.119. So the slip will be 0.09. That's the slip. And then second part is to calculate the rotor speed. So you have the synchronous speed, that's 1,500, and the rotor speed will be 1 minus s times synchronous speed. So that will be 1 minus 0.09 times 1,500. Which is 1365 RPM, that's the rotor speed. Third part of that, calculate the useful output torque produced by the motor. So that part is just to figure out whether you've understood the concept of output power, electromechanical power developed in the motor, and how the rotation losses subtract from that to produce the output power. So effectively you need to pick one of these numbers. So we were just checking whether you know what the correct number you need to pick from these. So it's the output power corresponds to the 800. So the output torque, useful output torque is the 8,000 divided by speed. So the rotor speed you calculated here. So that will be 1365 times 2 pi over 8,000 divided by this. So this is in watt, this is in radians per second, and this value will be the output torque. So we have 55.966 Newton meter useful output torque. Last part of that question. So do you have any issues with the previous parts? No? So the last part is, it is VOF control, it is required to supply the same torque at a speed of 1065 RPM using VOF control. Determine the supply voltage and frequency required to achieve this speed and torque condition. So it's pretty much the same concepts we discussed before. We have, let's say if you look at the torque speed profile, for 50 Hertz you have 1500 here and 1600, 1065 somewhere here, 365, and it's producing 55.966 Newton meter. That's the original operating point, and we need to change frequency and voltage such that you operate this at the same torque, and you have a rotor speed of 1065 RPM. So here you have a slip of, let's say, 1500 minus 1365, you have 135 slip. So the slip is 135 RPM slip speed. So these are two identical triangles. So here you have the same slip, 135 RPM. So the synchronous speed will be 1065 plus 135.